Picture this: a black hole, hungry and ancient, tearing apart a star so massive it could outshine millions of suns. In a fraction of a second, it unleashed a burst of energy 400 billion times greater than our Sun, enough to power an entire galaxy for millennia. The violence was so immense, it sent a shock wave racing through space at 1/5 the speed of light, a cosmic ripple tearing through the fabric of the universe. But here's the strange part: months later, astronomers detected helium hurtling away at speeds that shouldn't exist, like a ghostly remnant of the star's core, defying the chaos. How could anything survive such a death? This isn't just a tale of destruction. It's a mystery written in the ashes of a star's final scream, hinting that even in the jaws of oblivion, something extraordinary might yet endure. In the vast, uncharted regions of the universe, a cosmic spectacle unfolded that defied expectations. Astronomers recently observed a black hole tearing apart a massive star, an event so powerful it briefly outshone billions of stars combined. But what truly stunned scientists was not just the violence of the destruction, but the eerie possibility that something endured. This event, dubbed the Whippet, has rewritten our understanding of how black holes interact with stars and what might survive their relentless hunger. Let me take you through the story of how a black hole shredded a super sun, the explosion that followed, and the astonishing hint that something may have lived to tell the tale. Black holes are among the most enigmatic objects in the cosmos. Their gravity is so intense that not even light can escape them, and when they encounter a nearby star, the outcome is often catastrophic. Stars are held together by their own gravity, but a black hole's tidal forces, its ability to stretch and tear objects apart, can overcome this. When a star strays too close, the black hole's gravity pulls it apart in a process called tidal disruption. The result is a violent, luminous explosion that can outshine entire galaxies for brief moments. These events are rare, but they offer a rare glimpse into the extreme physics of black holes and their interactions with stars. The Whippet, however, was unlike anything seen before. The black hole in question was likely several times more massive than the Sun, and the star it consumed was no ordinary star. It was a super-sun, a massive star with a mass far exceeding that of our own Sunday. Such stars are rare, but when they do exist, they burn brightly and die violently. When the black hole encountered this star, the result was a cataclysmic event. The star was shredded, its material torn apart by the black hole's immense gravity. This process released an enormous amount of energy, equivalent to about 400 billion times the energy our Sun produces in its entire lifetime. For a brief moment, the explosion outshone billions of stars, making it one of the most energetic stellar explosions ever recorded. The destruction was not immediate. As the black hole pulled the star apart, it created a swirling disk of gas and debris around itself. This disk, heated by the immense gravitational forces, emitted intense radiation across the electromagnetic spectrum. The energy released was so powerful that it sent a shock wave racing outward at 1/5 the speed of light. This shock wave was a visible signature of the event, a wave of high-energy particles and radiation that swept through space. For months, astronomers tracked this shock wave, measuring its speed and intensity. What they found was both astonishing and puzzling. The shockwave carried with it a strange, unexpected component: fast-moving helium. Helium is a light element, typically found in the outer layers of stars. When a star is torn apart by a black hole, the debris is expected to be a mix of elements, but the presence of fast-moving helium was unexpected. Normally, such helium would be dragged into the black hole's disk or dispersed in a more chaotic manner. Instead, this helium was moving at an unusually high velocity, suggesting it had been accelerated by some mechanism not yet understood. This observation raised a tantalizing question: could a fragment of the star, or something else, have survived the destruction? The idea that something might have survived the tidal disruption of a star is both surprising and profound. Stars are not solid objects, they are held together by gravity and nuclear fusion. When a black hole tears a star apart, the material is typically shredded into a disk and consumed. But in the case of the Whippet, the presence of fast-moving helium hinted at a different possibility. Perhaps a portion of the star's material was not fully consumed, or perhaps some structure within the star remained intact. The helium's unusual speed suggested it had been propelled outward by a force stronger than the black hole's gravity alone. This could mean that a fragment of the star, or even a remnant of its core, was somehow preserved. To understand why this is significant, we need to consider what happens when a star is torn apart by a black hole. The process is not like a simple collision, it's a slow, gravitational dance. As the star approaches the black hole, its material is stretched and pulled apart, forming a disk of gas that spirals inward. This disk heats up, emitting radiation that can be detected by telescopes. However, the material in the disk is typically a mix of elements, including hydrogen, helium, and heavier elements. The presence of fast-moving helium in the Whippet's aftermath suggests that some of this material was not just pulled into the disk but was instead accelerated outward. This could indicate that a portion of the star's material was not fully incorporated into the disk, or that some structure within the star resisted the black hole's pull. The possibility that a fragment of the star survived the destruction is not just a curiosity, it has profound implications for our understanding of black hole interactions. If a star can shed a part of itself and have that material survive, it challenges our assumptions about how tidal disruption events work. It also raises questions about what happens to the material that is not consumed. In most cases, the debris is thought to be swallowed by the black hole or dispersed into space. But the Whippet's helium suggests that some material might be ejected with enough energy to escape the black hole's gravitational pull. This could mean that the event produced not just an explosion, but a complex interplay of forces that allowed some material to be propelled outward. The survival of this material is also intriguing because it hints at the possibility of a more complex structure within the star. Stars are not uniform, they have layers, with different elements and temperatures. The core of a star is dense and hot, while the outer layers are cooler and less dense. If the black hole's tidal forces were strong enough to strip away the outer layers, it's possible that the core, or a part of it, was left behind. Alternatively, the helium could have been part of a more structured remnant, such as a dense clump of material that resisted the black hole's pull. This would be a rare case where a star's material did not simply disintegrate but instead formed a distinct, surviving structure. The implications of this discovery stretch beyond the immediate event. If parts of a star can survive a black hole's tidal disruption, it could mean that similar events in the past might have left behind remnants that we have yet to detect. These remnants could be sources of unusual emissions or even new types of celestial objects. The Whippet's helium, moving at an unexpected speed, serves as a clue that such remnants might exist. It also suggests that our models of tidal disruption events may need to be refined to account for the possibility of surviving material. This could lead to new theories about how black holes interact with stars and what happens to the material they consume. But why is this discovery so surprising? For decades, astronomers have studied tidal disruption events, but they have typically focused on the energy released and the radiation emitted. The idea that a portion of the star might survive is a new twist. It challenges the notion that the destruction of a star by a black hole is a complete and irreversible process. Instead, it suggests that some material might be preserved, creating a new kind of cosmic phenomenon. This could also have implications for the study of stellar remnants and the formation of new objects in the aftermath of such events. The Whippet's helium is not just a curiosity, it's a piece of a larger puzzle. By studying the motion and composition of this material, astronomers can gain insights into the physics of tidal disruption events. The fast-moving helium suggests that there were forces at play beyond the simple gravitational pull of the black hole. These forces could be related to the magnetic fields of the black hole, the rotation of the star, or the complex dynamics of the debris disk. Understanding these factors could help scientists predict how other tidal disruption events might unfold and what kind of remnants they might leave behind. In the broader context of astrophysics, the Whippet represents a rare opportunity to observe the extreme conditions that exist near black holes. These environments are among the most extreme in the universe, with gravity so strong that it warps spacetime itself. By studying events like the Whippet, scientists can test theories about how black holes behave and how they interact with their surroundings. The survival of some material from the star could also provide clues about the behavior of matter under such extreme conditions, offering a glimpse into the fundamental forces that govern the cosmos. As we continue to explore the universe, events like the Whippet remind us that the cosmos is full of surprises. The destruction of a star by a black hole is a violent and dramatic event, but it also offers a window into the complex physics of these interactions. The survival of some material, even in the face of such overwhelming forces, challenges our understanding and opens new avenues for research. The Whippet's fast-moving helium is a tantalizing hint that the universe may still hold secrets waiting to be uncovered. And as we look to the future, we can only wonder what other cosmic mysteries await discovery. In the vast, uncharted regions of the cosmos, where the laws of physics bend and break, a cosmic drama unfolded in 2026. Astronomers, peering into the depths of space with instruments designed to capture the faintest whispers of the universe, witnessed an event so violent it defied imagination: a black hole tearing apart a star so massive it was once thought to be a super-sun. This event, dubbed the Whippet, became one of the most extraordinary celestial phenomena ever recorded. But how did scientists come to understand this catastrophic collision? How did they piece together the story of a star's destruction and the strange remnants that might have survived? Let's step into the lab of discovery and follow the trail of clues left behind by the universe itself. The journey began with a burst of light so intense it outshone entire galaxies. The initial detection came from a network of space-based observatories, including the James Webb Space Telescope, JWST, and the European Space Agency's XMM Newton satellite. These instruments, tuned to detect the faintest signals across the electromagnetic spectrum, were designed to peer into the early universe, but they also had the sensitivity to catch the sudden flare-up of a stellar death. The data came in as a flash of energy, so bright it was visible even in the crowded light of our own galaxy. This wasn't just a supernova, it was something far more extreme. The energy released was estimated to be 400 billion times that of our Sun, a figure so staggering it could briefly outshine all the stars in the Milky Way combined. The shock wave, propelled at 1/5 the speed of light, raced outward like a cosmic tsunami, tearing through the fabric of space. But how did scientists confirm this wasn't just a random burst of energy? The answer lies in the meticulous work of astronomers who analyzed the light signature. Using spectroscopy, they broke down the incoming radiation into its component wavelengths, revealing the fingerprints of elements being ejected from the event. The data suggested something unusual: the presence of a black hole's gravitational pull, which had shredded the star into a disk of gas and debris. This disk, heated to millions of degrees, emitted X-rays and gamma rays, confirming the presence of an accretion disk, a telltale sign of a black hole. Yet, the true mystery deepened when, months later, astronomers noticed something unexpected. Amid the debris, they detected fast-moving helium, moving at speeds that defied the expected chaos of a stellar explosion. This helium, traveling at a fraction of the speed of light, hinted at the survival of some structure, perhaps a fragment of the star itself, held together by forces yet to be understood. To uncover the story behind this helium, scientists turned to a constellation of telescopes and observatories, each with its own unique capabilities. The Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile, with its array of radio dishes, captured the faint radio waves emitted by the expanding debris. These waves, though invisible to the naked eye, provided a map of the material's motion, revealing its velocity and distribution. Meanwhile, the Chandra X-ray Observatory, orbiting Earth, tracked the high-energy emissions from the black hole's accretion disk, offering insights into the gravitational forces at play. On the ground, the Very Large Telescope, VLT, in Chile and the Keck Observatory in Hawaii provided optical data, allowing astronomers to measure the precise movement of the helium and its interaction with surrounding interstellar gas. Each observation added a new layer to the puzzle, building a picture of the event's aftermath. The timeline of discovery was as intricate as the event itself. The initial detection in 2026 was just the beginning. Over the following months, astronomers worked tirelessly to analyze the data, cross-referencing observations from multiple instruments to ensure accuracy. The helium's movement, first noticed in late 2026, required months of follow-up. By early 2027, the team had compiled enough data to confirm its unusual speed, far exceeding what would be expected from a typical supernova. This anomaly sparked a flurry of hypotheses. Could the helium be part of a surviving stellar remnant? Or was it a product of the black hole's gravitational influence, somehow preserving a fragment of the star's core? The answers lay in the data, but the process of sifting through it was as much about patience as it was about precision. One of the key breakthroughs came from the use of adaptive optics, a technology that allows ground-based telescopes to compensate for atmospheric distortions. By using deformable mirrors that adjust in real time, astronomers could capture sharper images of the region, revealing details that would have been impossible to see otherwise. These images showed the helium's trajectory, its path bending slightly as it interacted with the surrounding medium. The data suggested that the helium was not just moving randomly but was being guided by some unseen force, possibly the magnetic field of the black hole or the remnants of the star's own magnetic structure. This hinted at a complex interplay between the black hole's gravity and the star's internal dynamics, a dance of forces that had left behind something extraordinary. The role of space-based observatories was equally critical. The James Webb Space Telescope, with its ability to detect infrared light, provided a unique perspective on the event. Infrared wavelengths, which are often obscured by interstellar dust, allowed scientists to peer through the debris and study the thermal glow of the expanding material. This revealed the temperature distribution of the gas, offering clues about its origin and the processes that had shaped it. Meanwhile, the Neil Gehrels Swift Observatory, designed to detect gamma-ray bursts, played a crucial role in tracking the initial burst of energy. Its rapid response allowed astronomers to capture the event in its earliest stages, providing a baseline for comparison with later observations. As the months passed, the team's analysis grew more sophisticated. They employed advanced computational models to simulate the event, testing various scenarios to explain the helium's behavior. These models incorporated data from all the observatories, creating a virtual reconstruction of the black hole's interaction with the star. The simulation showed that the star's core, though shredded, might have retained enough mass to form a dense, compact object, a stellar remnant that could still emit radiation. This remnant, perhaps a neutron star or a black hole itself, might have been the source of the helium's unusual motion. The models also suggested that the black hole's spin and magnetic field could have influenced the debris, creating a complex web of interactions that defied simple explanations. The confirmation of the helium's survival came not from a single observation but from the convergence of multiple lines of evidence. The data from ALMA, Chandra, and the VLT all pointed to the same conclusion: the helium was moving at a velocity that could only be explained by the presence of a structured, surviving object. This object, though fragmented, had retained enough coherence to influence the surrounding material. The implications were profound. It suggested that even in the face of a black hole's relentless gravity, certain structures might endure, challenging our understanding of stellar destruction. The survival of this helium hinted at the possibility of a new class of cosmic phenomena, where the remnants of a star's death could still play a role in the universe's ongoing story. The process of discovery was as much about collaboration as it was about technology. Astronomers from around the world shared data, cross-checking results, and refining their models. The sheer scale of the event required a global effort, with observatories on every continent contributing to the analysis. This collective work underscored the power of modern astronomy, where the vastness of space is no longer a barrier but a canvas for exploration. Each instrument, from the ground-based telescopes to the orbiting satellites, played a vital role in unraveling the mystery, demonstrating how humanity's quest to understand the cosmos is as much about teamwork as it is about innovation. In the end, the story of the Whippet is a testament to the resilience of scientific inquiry. It began with a single burst of light, a flash so intense it defied comprehension, and evolved into a multi-year investigation that pushed the boundaries of our knowledge. The survival of the helium, though still a mystery, has opened new avenues for research, challenging scientists to rethink the fate of stars in the face of black hole encounters. As the data continues to be analyzed, the Whippet stands as a reminder that even in the most violent cosmic events, there is always more to discover, a promise that the universe, in all its complexity, will continue to surprise us. Astronomers have witnessed a black hole violently shredding a massive star, creating one of the most energetic stellar explosions ever observed. The event, nicknamed the Whippet, briefly released about 400 billion times the sun's energy and sent a shockwave racing outward at 1/5 the speed of light. Months later, scientists spotted unexpectedly fast-moving helium, suggesting that some structure may have survived the destruction. This part of our deep dive into a black hole shredded a super-sun, but something strange may have survived focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, astronomers have gazed into the cosmos, piecing together the violent and mysterious forces that shape the universe. The story of black holes and their encounters with stars is one of the most dramatic chapters in astrophysics, a tale that has evolved dramatically since the early days of modern astronomy. It began in the 1960s, when the theoretical foundations of black holes were first solidified. Albert Einstein's equations of general relativity, published in 1915, had hinted at the existence of these cosmic monsters, regions of space where gravity is so intense that not even light can escape. But it wasn't until the 1960s and 1970s, with the work of physicists like John Wheeler and Stephen Hawking, that black holes became more than just mathematical curiosities. They were real, and their influence on the universe was beginning to take shape. Yet, for all their theoretical weight, black holes remained elusive. Until the 1970s, no one had directly observed one. The first real evidence came in the form of X-ray emissions from a distant region of space, which hinted at a massive, invisible object pulling in nearby material. This was the birth of the first black hole candidate, Cygnus X1, a discovery that marked the start of a new era in astronomy. But even as scientists began to accept black holes as real, the question of how they interacted with stars remained unanswered. The idea that a black hole could tear apart a star was still speculative. It wasn't until the 1980s that astronomers started to consider the possibility. Theoretical models suggested that if a star ventured too close to a black hole, its immense gravity could stretch and shred the star, a process now known as tidal disruption. However, these events were thought to be rare and difficult to observe. The first confirmed tidal disruption event wasn't detected until the 1990s, when astronomers observed a sudden flare of light from a distant galaxy. This was a breakthrough, but it was still a rare occurrence. The tools of the time, like ground-based telescopes and early space observatories, were limited in their ability to capture the full scale of such events. The 2000s brought a new wave of technological advancements. The launch of the Chandra X-ray Observatory in 1999 and the Swift Gamma-ray Burst Explorer in 2004 allowed scientists to detect high-energy emissions from distant cosmic events with unprecedented precision. These instruments revealed that tidal disruption events were more common than previously thought, and that they often produced spectacular displays of light and energy. One of the most striking discoveries was the detection of light echoes from disrupted stars, which provided clues about the structure of the accretion disks around black holes. Yet, even with these tools, the full picture remained incomplete. The 2010s marked a turning point. The discovery of gravitational waves by the LIGO and Virgo collaborations in 2015 opened a new window into the universe, allowing scientists to observe the mergers of black holes and neutron stars in real time. These observations confirmed that black holes could exist in pairs, and that their collisions released immense amounts of energy. But while these events were dramatic, they were still different from the tidal disruption of a star. The 2020s brought even more progress. The James Webb Space Telescope, launched in 2021, began to revolutionize our ability to study distant galaxies and their stellar populations. Its infrared capabilities allowed astronomers to peer through cosmic dust and observe the faintest objects in the universe. This was critical for understanding events like the Whippet, which occurred in a distant galaxy and required sensitive instruments to detect its aftermath. Meanwhile, advances in computational modeling and data analysis techniques enabled scientists to simulate the complex physics of tidal disruption events with greater accuracy. These simulations helped predict the kinds of emissions that would result from a star being torn apart, providing a framework for interpreting observational data. By the early 2020s, the field had reached a critical juncture. Astronomers had accumulated a wealth of data on tidal disruption events, but many questions remained. How do these events evolve over time? What happens to the material that is torn from the star? And perhaps most intriguingly, could anything survive the immense forces of a black hole's grasp? The Whippet, observed in 2026, was the latest chapter in this long story. It was not just another tidal disruption event, it was a moment that brought together decades of theoretical work, observational advancements, and technological innovation. The detection of fast-moving helium months after the event suggested that some structure might have endured the destruction, challenging previous assumptions about the inevitability of a star's demise in such encounters. This discovery was a direct result of the cumulative efforts of astronomers over the past several decades, each building on the knowledge of the last. The historical context of this moment is not just about the past, it is a testament to how science progresses through curiosity, persistence, and the relentless pursuit of understanding. As we look to the future, the Whippet serves as a reminder that the universe is still full of mysteries waiting to be uncovered, and that every new observation brings us one step closer to unlocking its secrets. When astronomers first observed the Whippet, they were struck by its sheer scale. A black hole, likely several times the mass of the Sun, tore apart a star so massive it could have been a super-sun, a star with a mass tens of times greater than our own. The energy released in that destruction was staggering, 400 billion times the luminosity of the Sun, a flash so bright it briefly outshone entire galaxies. The shock wave that followed raced outward at 1/5 the speed of light, a speed so extreme it defied expectations. But what truly unsettled scientists was what came next. Months later, they detected something unexpected, helium moving at speeds far beyond what should have been possible in the aftermath of such a violent event. This anomaly has left astronomers grappling with a question that feels almost like a riddle. If a black hole tore apart a star, what could possibly survive? And if something did, what does it tell us about the nature of destruction, and perhaps, the resilience of the universe itself? The helium's speed, over 10,000 kilometers per second, was unlike anything seen in stellar debris before. In most tidal disruption events, where a star is shredded by a black hole, the remnants are scattered in a chaotic dance of gas and plasma, gradually slowing as they lose energy. But this helium was moving at a pace that suggested it had been propelled by an immense force, something far more powerful than the shock wave alone. Some scientists suspect it might have been ejected by the black hole's intense gravity, but the exact mechanism remains unclear. Others propose it could be part of a structure that survived the destruction, a remnant of the star's core, or perhaps a fragment of its outer layers that somehow escaped the black hole's grasp. Yet, if the star was fully shredded, how could any part of it retain enough energy to move at such speeds? The helium's presence challenges the assumption that tidal disruption always leads to complete annihilation. One of the most intriguing possibilities is that the helium isn't just debris, it might be a remnant of the star itself, a piece of its core that somehow escaped the black hole's grip. Stars like the one in the Whippet are thought to have dense, iron-rich cores, and if the black hole's tidal forces didn't completely tear those apart, perhaps a fragment remained. But how could such a dense core retain enough energy to propel itself at such high speeds? Some researchers suggest it might have been accelerated by magnetic fields or radiation pressure, forces that could act as a slingshot in the extreme environment near a black hole. However, these theories are speculative. The helium's exact origin remains a mystery, and its speed raises questions about the physics of tidal disruption itself. If the black hole's gravity could eject material at such velocities, what does that mean for the structure of spacetime near these cosmic monsters? Could it hint at new physics beyond our current understanding? The debate over whether the helium is a remnant or simply debris has sparked a broader discussion about the limits of destruction. For decades, astronomers have assumed that when a black hole tears apart a star, the result is total annihilation. The star's material is stretched into a stream, pulled into the black hole's accretion disk, and eventually consumed. But the Whippet suggests that perhaps this isn't always the case. If the helium survived, it implies that some parts of the star might have escaped the black hole's gravitational pull, either by being flung outward or by forming a structure that resisted the tidal forces. This challenges the traditional view of tidal disruption and opens the door to new models of how stars interact with black holes. Could there be cases where a star isn't fully destroyed, but instead leaves behind a fragment that continues to orbit the black hole? Or maybe the helium is part of a larger structure, like a disk or a jet, that formed in the chaos of the event? These questions are pushing scientists to rethink the boundaries of what we know about stellar death and black hole interactions. Another layer of mystery lies in the sheer energy of the Whippet itself. At 400 billion times the Sun's luminosity, it was one of the most luminous stellar explosions ever observed. For comparison, the most energetic supernovae release about 10 billion times the Sun's energy, and gamma-ray bursts, which are among the most powerful explosions in the universe, typically release around 100 billion times the Sun's energy. The Whippet's brightness defies existing models of stellar explosions, suggesting that the black hole's presence may have amplified the event in ways we don't yet understand. Some scientists propose that the black hole's tidal forces could have compressed the star's material, triggering a runaway nuclear reaction that released an unprecedented amount of energy. Others argue that the shock wave itself might have interacted with the surrounding interstellar medium, creating a feedback loop that intensified the explosion. But even if these theories are correct, they don't explain the helium's speed. The connection between the explosion's energy and the helium's motion remains an open question, and without more data, it's hard to say which mechanism is at play. The survival of the helium also raises questions about the nature of the black hole itself. Black holes are often thought of as insatiable entities, devouring everything that comes too close. Yet the Whippet suggests that even in their most violent encounters, they might not always consume their victims completely. If the helium is a remnant, it could mean that the black hole's event horizon, its point of no return, didn't fully engulf the star's outer layers. This would imply that the black hole's gravitational pull, while immense, isn't absolute. It also raises the possibility that other stars in similar encounters might have left behind fragments or structures that could be detected in the future. But how common are such events? Are they rare anomalies, or do they represent a more frequent interaction between black holes and massive stars? The answer could depend on the demographics of stellar populations in the universe. If massive stars are more common in certain regions, or if black holes are more prevalent in those areas, the Whippet might be just one of many such events waiting to be discovered. For now, the Whippet remains a puzzle, one that scientists are working to unravel through observations and simulations. Telescopes like the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory are already being used to study the aftermath of tidal disruption events, and future missions may provide even more detailed data. But even with these tools, the question of what exactly happened in the Whippet's case is far from settled. The helium's speed, the explosion's energy, and the possibility of a surviving structure all point to a complex interplay of forces that we're only beginning to understand. Some researchers are even speculating that the helium could be part of a larger phenomenon, like a relativistic jet or a magnetic field that somehow anchored the material to the black hole. These ideas are still in their infancy, but they highlight how much we have to learn about the extreme environments around black holes. In the end, the Whippet isn't just a story about a star being destroyed, it's a window into the fundamental forces that shape the universe. It challenges our assumptions about what happens when a black hole meets a star, and it hints at the possibility that even in the most violent cosmic events, something might endure. Whether that something is a remnant of the star, a fragment of its core, or a structure we've yet to imagine, the Whippet reminds us that the universe is full of surprises. As scientists continue to study this event, they're not just trying to solve a mystery, they're expanding the boundaries of what we know about the cosmos. And in doing so, they're uncovering new questions, ones that may take decades or even centuries to answer. For now, the Whippet stands as a testament to the power of observation and the enduring curiosity that drives scientific discovery. Astronomers have witnessed a black hole violently shredding a massive star, creating one of the most energetic stellar explosions ever observed. The event, nicknamed the Whippet, briefly released about 400 billion times the Sun's energy and sent a shock wave racing outward at 1/5 the speed of light. Months later, scientists spotted unexpectedly fast-moving helium, suggesting that some structure may have survived the destruction. This part of our deep dive into a black hole shredded a super sun, but something strange may have survived focuses on. Explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Astronomers have witnessed a black hole violently shredding a massive star, creating one of the most energetic stellar explosions ever observed. The event, nicknamed the Whippet, briefly released about 400 billion times the sun's energy and sent a shock wave racing outward at 1/5 the speed of light. Months later, scientists spotted unexpectedly fast-moving helium, suggesting that some structure may have survived the destruction. This part of our deep dive into a black hole shredded a super-sun, but something strange may have survived focuses on. Briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.